everyone. Good morning, all of you. Today we will discuss about the chemical kinetics, another important chapter of physical chemistry, right? Then later I will take electrochemistry. Chemical kinetics is another important chapter of the physical chemistry in which we talk about the rate of the reaction, right? Speed of the reaction, and the factors that affect the speed of the reaction and the mechanism, why it is slow or why it is fast, about everything concerned to rate of the reaction, right? There are some theories which explains about the speed of the reaction, right? So the three chapters which are important in chemistry are, one is thermodynamics, which tells about the feasibility of the reaction, whether the reaction occurs or not. So thermodynamics tells about the speed of whether the reaction is feasible or not. Suppose if you want to know whether the graphite can be converted into diamond, okay, this is a change, physical change. Whether this is feasible or not, what we have to do? We have to find out the Gibbs free energy change of the process, right? So, okay, right. I think I was not wearing the mic, whether it was feasible, whether it was heard or not, I don't know. Let me tell more once again about it. So in the chemistry, this is important to know about whether the process is feasible or not. The process is feasible. To test that whether the process is feasible, then we have to check Gibbs free energy change. If the Gibbs free energy change is negative, then reaction is feasible. That is denoted as delta G, right? Thermodynamics, right? Now, what is another thing that is important is extent to which the reaction proceeds. Okay, extent to the reaction won't mean that reaction will complete 100%. Many reactions do not go for completion. So extent to what the reaction occurs is determined by equilibrium constant. Equilibrium constant, right? So equilibrium is another chapter. By knowing the Kc value, by knowing equilibrium constant value, Kc value, we can able to determine that. Okay. By Kc value, we can able to determine that equilibrium. Right. For example, food gets spoiled. Food gets spoiled. So for this, delta G is negative, right? But how rapidly food gets spoiled? So this is the concern of how fast the rusting of iron takes place. These are the scopes of chemical kinetics. So these questions are answered by the chapter chemical kinetics. And why so? Right. So let us know about the chemical kinetics. Chemical kinetics is study of rate of reaction and the reaction rate and the mechanism. It also describes the speed or the rate of the reaction. The reaction types, slow, fast, and moderate reactions. See, some reactions are very, very slow. For example, rusting of iron is a slow process. And some reactions are very fast. Suppose in your chemistry laboratory, if you have taken barium chloride, a solution of barium chloride, in one test tube and another test tube sodium sulfate, say, and you add one test tube, the solution, if you mix it, immediately they give precipitate of barium sulfate. Barium chloride plus sodium sulfate will give you precipitation of barium sulfate, indication of the sulfate group. So this reaction occurs in a very fraction of second. I mean, the reactions are very, very fast. These reactions are ionic reactions, and ionic reactions are usually very fast. And the reactions which are having the covalent bonds, the compounds having covalent bond, then covalent bonds are to be broken and the new covalent bonds are to be formed. For this, some energy considerations are necessary for this. So speed of the reaction depends upon all such matter. So the reaction type slow, fast, or moderate, we can able to think about what could be the bonding between the bonding in the molecules or reacting species. That's why it is necessary to understand about it. Now, conditions by which reaction rate can be altered. Reaction rate can be altered in an industrial process. Getting the product is an important thing. Okay, so in the process of getting ammonia, right? So after dealing with nitrogen, after getting nitrogen and hydrogen and get the ammonia, if the rate of the reaction is very slow, then this is not a profitable business. What we want is we get more and more ammonia with the same reactant N2 and H2. What are the conditions by which we can able to get more ammonia? Therefore, the rate can be altered. Whether the rate can be altered, even though we use catalyst, but the conditions to use the catalyst is also a factor to be considered, and this deals with this. Chemical kinetics deals with it. Okay, there are slow reactions and the fast reactions, but in this chapter we deal more with those who are moderately fast reactions. We deal with moderately fast reactions, right? So what is the rate of the reaction? Rate of the reaction can be defined as the change in concentration of the reaction or product per unit time. Change of concentration of the reactant. Just as we measure the speed of a bus, right? Speed of a vehicle, right? If a vehicle moves 30 kilometer in 1 hour, say 30 kilometer in 1 hour, then 30 kilometer divided by 1, that is the speed of it. If it moves 30 kilometer in 30 minutes or half an hour, then 30 divided by half, that is 60 kilometer hour, is its speed. Same way, what is moving here? The moving one in the reaction is the reactant, the quantity of the reactant, right? Concentration of the reactant decreases and the concentration of the product increases. So from this point of view, we have to see. So rate of the reaction is concentration of the reaction product per unit time. How much concentration has changed in a unit period of time? Maybe 1 second, 1 minute, or 1 year, depends. Right. So rate of the reaction, we can write this formula. Rate of the reaction, change of concentration of the reactant by change in time. Okay, these are the things that we have learned. It can be expressed in terms of reactant or it can be expressed in terms of product. Right. Now, a rate of a chemical reaction, consider the reaction assuming the volume of the system is remained constant. Assume that volume of the system remains constant, right? So this is the one that we consider. Rate of reactant product, if this is the arbitrary reaction, R represent reactant and P represent product. Then change in concentration of the reactant. What is change in concentration of reactant represented? Delta R. Always concentration is represented in square bracket. Change of concentration is R2 minus R1. Right. Change in concentration of the product, delta P. So this is P2 minus P1. Where is concentration of P2 at a time T2, we can say. Right. And concentration of the P at the time T1. So change in time delta t, we use T2 minus Tm. Suppose it has started from 2 seconds. After 2 seconds, if it has started then ended 10 seconds, then 8 minus 2, that is 10 minus 2, that is 8 seconds is the delta t. So concentration is molar concentration. This is the one which we use, right? Square bracket is being used. Therefore, the expression can be written in this way. Rate of the reaction is minus delta R by delta T and minus plus delta P by delta T. For this reaction, mathematically it can be represented like this. Now question is, why this minus sign? Minus sign. The rate is always positive, right? Rate is always positive one. Rate of a reaction is positive. Now, if you take reactant to R2 minus R1, reactant after time t has decreased. So R2 is smaller than R1. Therefore, R2 minus R1 become a negative one. So to make it positive, we have to have the sign of negative so that these two are equal. So negative of negative we get delta R. Delta R is always taken as R2 minus R1, right? Therefore, it is negative sign is being given, right? Okay. Now, rate of disappearance of reactant, it can be written in another way. Rate of disappearance of reactant. Okay. So what is minus delta R by delta T? What exactly we mean is minus delta R is decrease of concentration of R, decrease of concentration of R, or it is a disappearance of rate of disappearance of the reactant. So the total one, this itself is disappearance, rate of disappearance of reactant is an important term. Divided by, okay, decrease of concentration of R by time taken. Negative sign indicates that concentration of the reactant decreases with time, right? Now, rate of appearance of product. Okay, the product is appearing more and more it becomes. So now there is a positive sign. Positive sign should be written here. So this is increase in the concentration of P by time taken. Therefore, delta P by delta T, right? For this generalized reaction, suppose if a generalized reaction, A moles of A, B moles of B giving rise to C moles of D and D moles of D. This A, B, C, D are stoichiometric coefficients, right? Then what way the rate expression can be given? Okay, so rate of the reaction can be written like this. This is minus 1 by A. That means stoichiometric coefficients are divided. Stoichiometric coefficients are divided, right? Stoichiometric coefficients are divided at each time. So B, whenever you are expressing disappearance of rate of disappearance of B with a negative sign, this is to be divided by B, right? Okay. Therefore, these things are to be kept in mind, right? So I give you some examples of chemistry, right? Suppose if it is PCl5 giving rise to PCl3 and Cl2. Suppose this is the reaction, say PCl5 giving rise to PCl3 and Cl2. 1 mole of PCl5 gives 1 mole of PCl3 and 1 mole of Cl2. Then the rate can be written as minus concentration of PCl5, decrease of concentration of PCl5, delta, and delta T. Delta concentration of PCl by delta T. This is in terms of reactant. This is equal to appearance of PCl3 by delta T, right? Or it is appearance of Cl2. The rate of disappearance of PCl5 is equal to rate of appearance of PCl3 and rate of appearance of Cl2. All the disappearance and the appearance are at equal extent. But suppose if this is the reaction, okay, NH3, okay, giving rise to N2 plus H2. right? For balancing this reaction, we need to take 2 here, right? 3. The stoichiometric coefficients are changed now. Stoichiometric coefficients are changed. Rate of disappearance of ammonia. When 2 moles of ammonia disappears, 1 mole of nitrogen is being formed. So rate of disappearance of ammonia is different than rate of appearance of nitrogen. When 1 mole of nitrogen is being formed, by the time 2 moles of ammonia is being dissociated. Therefore, rate of disappearance and rate of appearance are not equal, right? So here, same time, when 1 mole of nitrogen is formed, 3 moles of hydrogen is being formed. Okay, so it follows the stoichiometry of this, right? Suppose if it is occurring to the 100% extent, say, this is the way that we think about. So the rate is defined for change for 1 mole of the substance. Therefore, if it is 2 moles, we divide it by 2. We divide this by 2. The stoichiometric coefficients are divided. Therefore, rate of disappearance of ammonia is to be divided by the stoichiometric coefficient, so that we will get the rate of the reaction. So rate of the reaction is, therefore, rate of the reaction, the rate of disappearance is minus delta A by delta T. That is to be divided by A, then we will get rate of the reaction. So rate of the reaction will become same. Rate of the reaction in terms of that will become same in this case. No, there are 2 kinds of rates, or the way that it can be expressed. One is average rate of the reaction and another is instantaneous rate. What is meant by average rate? Average rate depends upon the change in the concentration of reactants or products and the time taken for that change to occur. Time taken for that change to occur. So usually we take larger span of time for considering average rate of the reaction, right? Average rate of the reaction takes large span of time. Okay. And instantaneous rate, what is instantaneous rate? Okay, our average is minus delta R. This is the way the expression that we are writing. What we have told so far is concerned with average rate. There is instantaneous rate of the reaction. Instantaneous rate, we mean the rate of the reaction at a particular moment of time is called instantaneous rate at a particular point of time. Okay, I can give the similar examples to explain about this average and instantaneous rate. Suppose if you are going in a car, okay, 100 kilometers in 2 hours, 100 by 2, that is 50 kilometers per hour is your average speed. You are taking total distance divided by total time taken by you. This is average speed. Suppose if you are if you want to find out speed of your car at the national highway where you are going, your speed may be more than the average, right? So this can be seen by the odometer or speedometer which is being there in the car, fixed in the car, right? So it may be 70 kilometers per hour, or when you are traveling inside the where the traffic is more, there your speed may be 20 kilometers per hour, right? That is the instantaneous speed. Okay, speed changes at a particular moment of time. What is the speed of it is determined, is called as instantaneous rate of a reaction. It is all mathematical advancement which made us to define in this way. So instantaneous rate of the reaction is denoted like this: rate instantaneous INS minus dr by dt. Dr, small change in the reactant, by a small change in the time. And a small change, almost a fraction of second, say, dr by dt or dp by dt. This is the rate expression. This is the rate expression or instantaneous rate expression we use to give some application. Okay, this is the differential form of rate expression. So differentiation and integration you have studied now, right? So there are integrated rate expressions also. So this is the differential form of rate expressions. So this is due to the mathematical advancement we are using such terms, and this is necessary for us. Then let us see in the graph. Let us see from the graph, right? So this is concentration of the reactants by time taken. Concentration of the reactant by time taken, and the graph is like this, correct? So it is changing. It is changing with the time. Okay, and you can find here that this is not touching. This means this much reactant may be remaining as this is about the equilibrium state. Okay, it won't come to the zero at all. Okay, at any point of time. Therefore, it won't touch. Therefore, you should draw in the same way, right? So how to find out the rate of the reaction from the graph? You can able to find out the rate of the reaction by using the graph, by taking the slope of it. Okay, so if you want to take the slope of it here, what you have to do is you have to draw a tangent. You have to draw the tangent to the curve. Then you can able to take up a triangle in which you can find y2 minus y1, and this is x2 minus x1. y2 minus y1 divided by x2 minus x1. This is the slope of the, and slope itself is the rate of the reaction, right? So average rate is minus delta R by delta T, because this y2 minus y1, okay, y2 minus y1 will be negative. Therefore, negative into negative becomes, it will positive, right? Rate instantaneous minus delta R by delta T. Okay, so this is nothing but negative of the slope. Slope is negative. Slope is negative because slope is negative is a downtrending curve. Therefore, it is negative, right? Now, from the point of view of product, this is increasing. The rate in the concentration of the product increases with time. So this is the concentration of the product. This is time, and the concentration of the product increasing. In the same way, when you want to find out the slope of it, take the tangent and take the slope of it, and you can find the rate instantaneous or rate average instantaneous dp by dt, that is slope. This is a positive slope. Slope is positive here, right? Okay, but question is the slope same at all the point of time? It is not so. So rate is not uniform throughout. If you take slope here, it may be more, and the slope here it is less, right? Therefore, the finding the rate of the reaction graphically like this is not accurate method. It is not an accurate method, right? Average rate, we won't get an accurate thing because it is different. Instantaneous rate, of course, we can take. Instantaneous rate we can take after 10 seconds of the start of the reaction. What is the rate of the reaction? We can able to understand by plotting such graph, plotting this graph. Okay, so there is again another thing that is necessary to be done for these experiments. We have to find out the concentration of the reactant or the concentration of the product when the reaction is going on. Okay, the spectro advances in science has made us to find out the concentration of the reactant at a particular time, right? So this graph can be drawn only when the concentration at a particular time is known, right? Now, check your understanding. In a reaction, 2A giving rise to products, right? 2A giving rise to products. The concentration of A decreases from 0.5 moles per liter to 0.4 moles per liter in 10 minutes. Calculates the rate during this interval. Calculate the rate during this interval. Come on, use your paper. First, write the expression. You can answer me if Okay. In a reaction, 2A giving rise to products. From the point of view of A, the concentration of A decreases. Concentration of A decreases from this to this in 10 minutes, right? But stoichiometric coefficient is being given. Okay. Rate of the reaction and rate of disappearance of A. You should be able to make the differences between these two clearly. So what is asked is rate of the reaction. Calculate the rate of the reaction. Therefore, rate of reaction is given by minus. Okay. Stoichiometric coefficients are to be divided 1 by 2. The stoichiometric coefficient is to be divided. Then delta A by delta T. Have you taken this too? Okay. Chances of forgetting is there. This is the way that you have to take minus. Okay. Final concentration divided minus initial concentration minus half. Final concentration is 0.4 minus initial concentration 0.5. Okay. Divided by time taken. So time taken is 10 minutes, right? 10. Okay. This is the calculation that you have to do, right? I think this is a simple calculation, and anybody who can able to say? Okay. So the answer is 5 into 10 to the power minus 3 moles per liter per minute. Moles per liter per minute, right? Okay, this is the way that you can do it. Right, this is the answer of it. Okay. Now ready for another question. For a reaction 2A plus B giving rise to 3C, rate of appearance of C at a time t is 1.3 into 10 to the power minus 4 moles per liter per second. Calculate at this time rate of the reaction and rate of disappearance of A. Yes. More likely the questions can be asked in this way. The questions can appear like this, okay, in the examination. 1, 2, the sub questions. So if it is a 2-mark question, then there will be 2 questions normally. In this way, the chemistry paper will be, right? Rate of the reaction, okay? So the answers are here. Okay, the rate of appearance of C at a time is being given, right? So we'll write the rate expression. Rate is equal to minus 1 by 2. Okay, I will write like this instead of writing minus 1 by 2. Okay, fine. 1 by 2 minus delta concentration of A by delta T. Okay, rate is equal to delta minus delta B by delta T, right? Both are the reactants, minus sign is to be taken, is equal to 1 by C, positive, this is positive, delta concentration of C by delta T. This is the expression for it. Now look at this. Rate of the reaction. Calculate the rate of the reaction. Rate of appearance of C. Rate of appearance of C. This is being given. Rate of appearance of C. Now, if this value is being given, how to find out the rate of the reaction? Rate of the reaction can be determined. Rate is equal to 1 by 3 of rate of 1 by 3 of rate of appearance of C. So knowing that the definition is important then. So 1.3 into 10 to the power minus 4. So divide that 1.3 by 3, right? This is the way we can able to get. Okay, therefore it is 4.33, you can say. Okay, 3 4s are 12, and this will become 10 to the power minus 5, right? You can do this calculation and say rate of disappearance of A. You have to find out rate of disappearance of A. So Students, see that this is rate of disappearance. Along with negative sign you have to take. This is rate of disappearance. This is the definition. Rate of disappearance is minus delta A by delta T. Once the rate is known, multiply this by 2. Multiply this by 2. This 2 is to be brought here, so that you will get rate of disappearance of A. So rate is already there, therefore it should be double of this. For double of this, it is 8.66. Okay, tallies. Okay. Now, what are the factors that affect the rate of the reaction, speed of the reaction? What do you think? So you have already thought about it, therefore let me take up in a not spending more time. Rate of the reaction depends upon experimental conditions and also concentration of the reactant. So if the concentration is changed, the rate of reaction changes. Pressure of the reactant in case of gaseous reactants, right? Nature of the reactant, it depends upon the nature of the reactant, and temperature and catalyst. Catalyst increases the rate of the reaction, but it won't affect the equilibrium state of the process. But catalyst increases the rate of the reaction. Temperature, whether temperature increases the rate of the reaction, the question arises if it is an exothermic process. If the process is exothermic, if the reaction is exothermic, still we need to supply heat. This will be answered by the temperature conditions. For the most of the reactions, we see that by increasing 10 degrees Celsius of temperature, the rate of the reaction is almost doubled. It is doubled. That means temperature of the reaction, even though it's exothermic or endothermic, it increases the rate of the reaction. So let us see from each of this point in detail. How and so? Nature of the reactants. So nature of the reactant is important in that way. Suppose NO plus O2 giving rise to NO2, say CO plus O2 CO2. Suppose there are two reactions which are of similar type. Okay, NO plus O2, NO2, and this is almost of the same type, but rate of the reaction is different. So it depends upon the nature of reactants. Even though reaction is almost same, but the nitrogen carbon is a difference. The rate is different because every atom bonds with the other with different energy, or the energy consideration we have to see. The breaking of bonds need different energy, and the formation of bond will release different amount of energy. Therefore, in total, the rate of the reaction will be different, and it affects nature of the reactant also affect the rate of the reaction. Now, okay, dependence of rate on concentration. Okay, how the rate is affected? How the rate is affected is determined by rate law. Rate law explains about how rate of the reaction is affected. The rate of the reaction is directly proportional to, if any arbitrary reaction, if you take, right? If you take any arbitrary reaction, A plus B giving rise to products, rate is directly proportional to concentration of A. Okay, concentration of A. So if I take A moles of A and B moles of B, what the rate law says, this may or may not be equal to that of A. That means that it is to be raised by some number like alpha. The concentration term is to be raised by some number. I have given as alpha here. This alpha may or may not be equal to A. Right. The stoichiometric coefficient and this alpha are different, may be different. And this is only determined experimentally. Okay. And rate also depends upon concentration of B. okay, to the power beta. Okay, so the expression can be done in this way. Rate law expression, rate is directly proportional to concentration of A to the power alpha and concentration of B to the power beta, right? Or rate of the reaction is equal to, whenever you convert into this sign, there will be a rate constant, right? K, A to the power alpha and B to the power beta. This is called rate constant. Okay. So the rate is directly proportional to concentration of reactant, right? So this alpha is determined, this is alpha is determined only experimentally. This alpha and beta are experimentally determined. Okay. What happened? Okay. Yeah. So again, the same way that what I have written, this is being taken here. For an arbitrary reaction, rate depends upon the concentration of A and concentration of B, reactants only. So rate of the reaction is, therefore, A to the power X and B to the power Y, or rate of the reaction can be written in this way. So alpha and beta are determined experimentally, where exponents X and Y may or may not be equal to the stoichiometric coefficients, right? So the law of mass action says that, law of mass action, which was considered earlier, this X and Y were replaced by the stoichiometric coefficients A and B. But later it is known that this law of mass action cannot be applied for every reaction. Therefore, this X and Y or alpha or beta, whatever that we write, may or may not be equal to the stoichiometric coefficients. So this generalization is being made. And this is called rate law. This is called rate law. What is rate law? Rate law is the rate of the reaction is directly proportional to product of concentration of the reactants, product of concentration of the reactant, each concentration term being raised by some numbers which are determined experimentally. Okay. So this is called rate law. Rate law. This is the word in words. Okay. K is rate constant. Okay. Now the rate of the reaction we already taken as minus dr by dt, minus is r as a reactant by dt, is equal to k into a to the power x and b to the power y. If you write the rate of the reaction in this way, combining both the equation, this is called differential rate equation. Differential rate equation. So instantaneous rate and the rate law expressions are combined. Okay. So K is a proportionality constant called as rate constant or velocity constant or specific reaction rate. Specific reaction rate. Now, how do you define the rate constant? Always there will be constant, proportionality constants, right? In the previous yesterday, that we have already seen that delta TB is equal to KB into molality, delta TF is equal to KF into molality, right? Here the expression is rate of the reaction, say rate is equal to K into A to the power X or B to. So every time I generalize this so that you can able to give the definition. Connection is low. Okay. Right. Maybe resolved. Right. So here what we have defined is bulioscopic constant is nothing but elevation in boiling point when molality of the solution is 1. So make the other factor as 1 along with it, one which is along with it, so that you can define it, right? Bulioscopic or molar elevation constant is elevation in boiling point of 1 molar solution. Cryoscopic constant is depression in freezing point of 1 molar solution. Similarly, can you able to define here? Rate constant is, rate constant is rate of the reaction when concentration of reactants are taken as unity. Make the concentration 1. 1 raised to x is 1, 1 raised to y is 1. Therefore, A and B, if they are unity, then you can define the rate constant, K value. Right? This is how you can able to define the rate constant. Right? Right. Now, what is rate law? The expression in which reaction rate is given in terms of molar concentration of the reactants, with each term raised to some power, which may or may not be same as the stoichiometric coefficients of the reacting species in a balanced chemical equation. Right. So in a general reaction, the rate of the reaction is equal to K into A to the power X, B to the power Y. Okay. For a reaction, A moles of K. Sometime we'll catch. Okay. Rate of the reaction, K into A to the power X, B to the power Y. K is rate constant, and A and B are 1 mole. Then rate of the reaction is K. This is how rate is being defined. This is what I told you. Reaction rate when when the concentration of the each reactant is unity. Okay. So the value of the rate constant is definite and constant for a particular reaction for a given temperature. So this value of the rate constant is same for a reaction, but it changes with temperature. This is the thing that you have to understand. Okay, so it is independent upon the concentration of the reactants, because it is already determined when the concentration of the reactants are 1. Therefore, it is independent upon the concentration of the reactants. Depends only upon the temperature and catalyst, right? Catalyst also changes that. So now, what is the order of the reactions? So we have written the rate law expression. For this reaction, right? So if it is the rate law expression, okay, where X and Y are the powers in the rate law expression, the sum of X plus Y is called order of the reaction. The sum of the powers of concentration of the reactant in the rate law expression is called order of the reaction, right? So X is the order of the reaction with respect to A, and Y is the order of the reaction with respect to B. This is the way we speak. X is the order of the reaction with respect to A, Y is the order of the reaction with respect to B, and X plus Y is the order of the reaction. Order of the reaction is X plus Y. So, okay, what are the other characteristics of order of the reaction? It can be determined experimentally. It can be 0, 1, 2, and even a fraction. It can be a fraction also. Order of the reaction can be a fraction, right? And the reaction are 0, first and second order reactions. So we call like that. If the order is 0, then we call it as 0 order reaction, right? 0 order reaction means that the rate of the independent upon the concentration of the reactants. Order of the reaction cannot be predicted by merely looking at the balanced chemical equation. It's important thing. So order of the reaction cannot be determined by the balanced equation, because stoichiometric coefficients may not tell about the X and Y value which are experimentally determined. Suppose NO2 plus F2 giving rise to NO2F, right? If this is the reaction, the rate expression is, in the rate expression, experimentally determined rate expression, we are having NO2 to the power 1 and F to the power 1. So sum of the exponents is 2. Therefore, it is a second order reaction. The stoichiometric coefficient is 2, but experimentally determined fact is there is power 1 only. Therefore, it is a second order reaction. So, the rate expression that we are writing only from the basis of experiment, but not merely by looking at the balanced reaction. Right. So, coming to this 3NO gas giving rise to N2O gas and NO2 gas, we find that rate is equal to K into NO square. Even 3 is there here, only 2 is there here. It is a second order reaction. It is a second order reaction. Right. Okay. For this reaction, 2NO2, the 2NO2 gas giving rise to 2NO and O2, the rate is NO2 whole square. It is also second order reaction. It is also second order reaction. So it is equal to this. Okay. It has come. Right. Okay. Now H2O2, 3I, 2H plus. Okay, it is a reaction involving 1 plus 3 plus 2, 5 reacting species. So rate of the reaction is H2O2 and I minus. H2O2, I minus only. It is not depend upon the H plus ion concentration at all. Right. So now the question arises, why it is so? Why it is so? So if the reaction is occurring like this, suppose if the reaction is occurring like this, that means the stoichiometric coefficient is being raised. That means it is an elementary reaction. If stoichiometric coefficient is being raised in the rate law expression, this is the elementary reaction. What is that elementary reaction? That reaction is occurring in single step. Okay, there is occurring in single step. But such reactions where stoichiometric coefficients are not being raised by the concentration term, that is a complex reaction. What we mean by the complex reaction is the reaction is not occurring in the same way as it is stated. It is a final reaction. There are reactions occurring in different steps. The reactions may occur in different steps. So it is a complex of all such reactions. So this is what the overall reaction is. That means it need to be explained through the mechanism. It need to be explained through the mechanism why it would have happened so. Right. Now for this, the H2O2 and I minus only is there, and one of the species is not involved at all. It is zero ordered with respect to H plus ion. It is zero ordered with respect to H plus ion. This is the way that we can say. Okay. So order of a reaction and the units of rate constant is again another important thing that we have to know. We can make a generalization. If the reaction is of nth order, then how do you find out the unit for K? So this A is A to the power n to be divided, A to the power n to be taken, and rate is expressed as concentration by time. Rate of the reaction is concentration, change of concentration per unit time. Therefore, concentration by time into, okay, it is divided by, means into 1 by A to the power. A is concentration to the power n. Therefore, what is the change here? K is nothing but concentration change 1 minus n, n is in the denominator, time to the power A per 1. Now you can tell me if it is a zero ordered reaction, that means n is equal to 0. If n is equal to 0, then concentration to the power n, that means moles per liter is the concentration to the power 1, and time to the power 1 minus 1. Moles per liter per second is the unit of zero ordered reaction. If it is first order reaction, then 1 minus 1 becomes 0. Then it is only per second. Per second is the unit of first order reaction. Okay, if it is a second order reaction, you can change the value, go on changing the value of N and moles per liter to the power that you are going to get, right? In that way, you can able to write the different units, right? For the second order reaction, this is moles per liter per second into 1 divided by moles per liter whole square. Therefore, per mole liter per second, per mole liter per second, or liter per mole per second. So this is the units of rate constants. Okay. So I was talking about elementary reaction, right? Elementary reaction. What is this elementary reaction? The elementary reactions are those which complete in one step. For example, decomposition of ammonium nitrite. Decomposition of ammonium nitrite, NH4NO2 gives N2 plus 2H2. Decomposition of dinitrogen tetroxide, N2O4 giving rise to 2NO2. So these are all occurring in one step. These are all occurring in one step, right? Decomposition of ammonium nitrite, decomposition of dinitrogen tetroxide, right? So the complex reactions, they are multi-step reactions where the products are obtained after completion of sequence of elementary reactions. There are sequence of reactions, and the sum of all these are reflected in a complex reaction. Biomolecular reactions involve simultaneous collision between the two species. Any bimolecular reaction, a bimolecular reaction, what we mean is, so two molecules collide each other to bring about the reaction. Okay. So dissociation of hydrogen iodide, 2HI giving rise to H2 and I2, we mean that HI, two molecules collide each other and bring about the reaction. Therefore, molecularity of this one is 2. Okay. So trimolecular reaction. Trimolecular reaction means, or termolecular reaction means, there is involvement, simultaneous collision between 3 reacting species. So 2 plus 1, O2, 3. So if the stoichiometry like this is an elementary reaction, and for the elementary reaction, the reaction is occurring in single step. And you can give the rate expression like this easily by looking at the reaction. If it is occurring in one step, then K into HI to the power 2. You can raise this particular stoichiometric coefficient to the concentration term. For the elementary reactions, we can write like this. Okay. So I hope you have understood now clearly why for some reactions the stoichiometric coefficients are written as a power of concentration term, and why not in some other reactions. So if the reaction is elementary, that means occurring in one step, so there is no hidden agenda or hidden reactions which we cannot able to see by looking at the balanced reaction, then we cannot able to write, we cannot consider the stoichiometric coefficients, right? So this is molecularity of the reaction. There is another term, molecularity of the reaction. What is meant by molecularity of the reaction? The number of species that collide each other to bring about the reaction. That is called molecularity of the reaction. Or molecularity of the reaction is simply the number of reacting species, that may be atoms, ions, or molecules. Atoms, ions, or molecules involving in an elementary reaction which must collide simultaneously, to bring about the reaction. So collision theory, there the scientists developed the collision theory in order to explain the reactions. What collision theory basically believes that the reaction occurs only when the species which are supposed to be undergoing reaction must collide each other. Okay, they collide each other effectively. So effectively, when it comes, the reaction conditions are applied. So when they collide each other effectively, then the reaction occurs. Okay, so let us consider this reaction. Ammonium nitrite is a unimolecular reaction, as I told you. Decomposition of HI is a bimolecular reaction. 2NO plus O2 giving rise to 2NO2 is a trimolecular reaction. So these are elementary reactions, and therefore elementary reactions we can able to see the unimolecular, bimolecular, termolecular reactions. Okay, if they are occurring in one step. right? So these are all experimentally determined only. By looking at the reactions, we cannot say that whether it is an elementary reaction or a complex reaction. Experimental determination will tell you what way the change of concentration will affect the rate of the reaction. Thereby, we can able to do that. So we'll take up some examples and we see whether it is how to determine the K value. By that, you can able to know whether it is a whether it is molecularity of the reaction can be found out or not. Right. Now, this is a question which is oftenly asked. Why the reaction having molecularity greater than 3 is rare? Why molecularity of the reaction? Why the reactions having molecularity greater than 3 is rare? So, what we mean by molecularity 3? Molecularity 3 means 3 molecules simultaneously have to collide of many number of particles, reacting particles, and 3 particles of different kind hit each other or collide each other effectively at a particular point of time. Since this is rare, therefore molecularity is also rare. Since the chances of collision and the reaction of the more than 3 molecules at a time is very less. The molecularity is greater than 3 is again in the presence of FeSO4 and H2SO4 will KCl and ferrous sulfate, ferric sulfate and H2O, right? In this reaction, how many reacting species are there? 1 plus 6 plus 3, 10. So 10 reacting species are there. Actually, it is a second order reaction. Can be explained the mechanism of the reaction. Okay. Let us take the decomposition of H2O2 to tell you about how exactly the mechanisms are explained. Right. H2O2 in the presence of iodide ion, alkaline medium and iodide ion, it undergo decomposition to give H2O and O2. Rate tells that rate of the reaction or differential rate equation says that this rate is depending upon K into H2O2 to the power 1 and I minus to the power 1. Even this I minus is not at all there in the product, but the concentration of I minus ion also determines the rate of the reaction. It is a strange thing. Then how to explain this? This reaction is first order with respect to H2O2 and I minus is first order with respect to both. Evidence suggests that the reaction takes place in 2 steps. Important. The reaction takes place in 2 steps. H2O2 plus I minus giving rise to H2O IO minus. So it initially reacts with I minus, right, to give H2O and IO minus, and H2O2 IO minus further again reacts to give H2O I minus and O2. So in the overall reaction, what we find is I minus and I minus can be cancelled, right? And IO minus and this can be cancelled, right? And the overall reaction is this. What I want to say here is the reaction may occur in 2 steps. Okay. Overall reaction is looking like this. But actual reaction occurs in 2 steps. And out of the 2 reaction, one may be slow and another may be fast. The slow reaction determines the rate of the reaction. Always in a process, slow one determines the rate of the reaction, right? Right. Okay. So to tell you that why that slow reaction determines the rate of the reaction, I will give some examples of it, right? Suppose the water is made to run in a pipe like this. Say, it is having different lets, and this let is of 1 inch. Okay. And this lead is having 2-inch, right? So there are chambers and water is made to move down from top to the bottom. The 3-inch lead is there, dia is there, from through which it can come and through which water can come, and this water can come. But the speed of the water moving down is determined completely by the smaller wall, or the dia of the wall is only 1 inch. This determines the speed of this, because even though the reaction may be coming, even though the water may be flowing more here because of the 3-inch lead, but it is controlled by this particular wall. Water gets stagnated here, right? So this is the way the slow step determines the rate. In the way, if one of the reaction is slow, then that determines the rate. And there are, you might have come across the movement of the vehicles in a city, right? If a heavy loaded truck is going in the way slowly and all other vehicles following that, they have to follow the speed of that vehicle only, right? Therefore, the slowest one determines the speed of other vehicles. In the same way, probably in the reactions also, the complex reaction is having one step which is slow, and that slow step determines the rate of the reaction, right? Right. So let us know more about molecularity of the reaction. Molecularity in case of a complex reaction, molecularity of the complex reaction has no meaning, because elementary reaction, which is a slow reaction, we cannot able to say. Therefore, molecularity has no meaning. The complex reaction is a series of 2 or more elementary reactions. So it completes in several steps. It completes in several steps. The slowest step or the slowest reaction determines the rate of the reaction. Molecularity of the slowest elementary reaction of a complex reaction is similar to that overall order of the complex reaction. So this point you have to understand: molecularity of a slowest elementary reaction of a complex reaction, that actually determines the order of the reaction. Okay, similar to overall order of the reaction. This is from that particular reaction, the stoichiometric coefficients are to be chosen for writing the order of the reaction. So molecularity versus order. So 2 terms. Is it confusing? Let us see which are the points to be considered. Molecularity is the number of atoms or ions or molecules that must collide with one another simultaneously so as to result into a chemical reaction. This is the definition of molecularity. What is order of the reaction? Order of the reaction, it is the sum of the powers of concentration terms on which the rate of the reaction actually depends, right? Or it is the sum of the powers of concentration terms in the rate law equation or expression. Molecularity of the reaction cannot be 0, because what it believes it is when the particles collide each other, particles like ions, atoms collide each other, then bring about the reaction. And for collision, it cannot be 0. 0 particles won't collide. Okay. Order of the reaction can be 0. Order of the reaction can be 0. Okay. It may not depend upon one concentration of one at all. That is order of the that is what we mean. So it is a theoretical concept. Molecularity is a theoretical concept. It is determined, order is determined experimentally. It is always a whole number. The overall molecularity of the complex reaction has no significance. Individual step is to be one molecularity. Order of the reaction is for overall reaction. Order of a reaction is for overall reaction. It is always overall reaction. Okay. So what we have studied so far is what we have studied. So to sum up, we have defined the rate of the reaction, right? Rate of the reaction and the We have considered what are the factors that affect the rate factor, how concentration of the reaction change, how concentration of the reaction affects the rate of the reaction, right? And in that, we have studied about the order rate law and order of the reaction and molecularity of the reaction, right? In the next phase, let us know about the integrated rate equation, right? And integrated equation for a zero order reaction and the half-life period of the zero order reaction, integrated rate equation for the first order reaction, half-life for the first order reaction, and what is meant by pseudo first order reaction. So about this, let us know about this. Why integrated rate expressions are essential? Integrated rate expressions are essential because the way that we are determining the rate graphically is not accurate. So by doing some mathematical interpretation, we can, or integration rate expressions, we can able to calculate rate of the reaction accurately, right? Integrated rate equation, the differential rate equation is written for a zero order reaction. Okay, integrated rate equation is equation obtained by integrating the differential equation to give the relationship between directly measured experimental data. It helps in determining instantaneous rate of the reaction. It helps in determining instantaneous rate of the reaction, right? So integrated rate equation for the zero order reaction and the first order reaction, let us find out this, or let us recall how this expression is being derived. Okay, so arbitrarily the reaction, let us consider the reaction R giving rise to P. R is a reactant, P is the product, right? Rate is directly proportional to concentration of the reactant to the power 0 because it is a zero order reaction. We have considered that. Okay, therefore we can write the differential equation in this way. Rate is equal to minus dr by dt k into r to the power 0. Right.
Sir, video is not
Now,
clear. Sir.
Video is not clear? You mean the slide is white background? Probably, is it so? Or is it issue of... okay. I think this expression may not be clear, right? Okay, I will write that. Okay. Okay, I'll just take it up. Just a minute. Okay. Okay. Okay, integration. So internet connection is unstable. This is what given. Yeah. Yeah. Okay. Yeah. So internet understand.
Network, sir.
Yeah, network is not is giving the message like that.
Okay, sir. Sir, please switch on the video of Zoom, sir. Zoom video, I will come to check.
Okay. You can close.
Go to whom, sir?
No, no, come.
Sir, can you off the Zoom video, sir?
Okay. Okay, fine. Okay, sir. Okay, fine. This is having some issue of, right? There was some issue of internet. Internet connectivity is changed. Right. Hope it is audible and visible, right? May I ask about the clarity from you? Anyone who can say? Okay. Right. I hope I'm audible. Okay. For a zero order reaction, right? For a zero order reaction, okay, the differential equation is written like this. Rate is equal to minus dr, if R is the reactant, by dt is equal to dr by dt is equal to K into concentration of R to the power 0. If R giving rise to P is an arbitrary reaction, then reactant giving the product, rate of change of R versus time. Okay, negative sign because it is a reactant. It is the differential rate equation. So we have to integrate this differential rate equation, right? For that, what we do is we start integrating this expression, integrating both sides. So integration of dr means with respect to R. Okay. So is equal to integration of K dt. This dt is to be transferred there. R to the power 0 is 1. Therefore, this is the expression. Integration of 1 dr. Probably now you know it because differentiation and integration is over. You can understand this chemical kinetics in a better way now. Because probably this chapter might have taught when the differentiation in the mathematics is not over. So what about the integration of 1 with respect to x? So this is x itself. In the same way, integration of 1 with respect to r, dr, is r itself. Okay. And integration of a constant is constant. K can be taken outside. Integration of 1 dt. Integration of 1 dt is t itself. And there is constant of integration that you have to write. Constant of integration. Right? So the expression takes in this way. Now, at the time, in order to find at the time t is equal to 0, at the time t is equal to 0, okay, so we consider the concentration of this r is 0, and this k into time t is 0 plus c. Therefore, this constant of integration is nothing but initial concentration. So it is nothing but initial concentration, right? Okay, right. Right. Now, let us have the same expression. Concentration of R is equal to KT plus C. If this is the expression, then, okay, this, right. Okay. Right. This concentration of R, KT, plus constant of integration is C. Constant of integration is C. But I have not taken the negative sign. This we have to consider minus dr. Minus dr is there. Therefore, minus r. And the concentration of C is also minus R0 because minus sign is ignored. It is concentration of a reactant. Therefore, minus sign is to be taken. Okay. So this expression, therefore, will be minus R is equal to KT plus C. Minus R is equal to where C is minus R0. So concentration of R naught. Right. So expression will become like this. Okay. Integration of minus 1 dr. Integration of minus 1 dr. Okay. This is minus 1. Consider as a minus 1 or 1 into minus dr. Right. So this is minus r kt plus c. So when time t is equal to 0, this t is equal to 0, k into 0, that is 0, c is minus r naught. Yes, minus r naught. Minus r naught is nothing but c value, constant of integration. So it is the initial concentration. So at the time t is equal to 0, what you have taken the reactant, the concentration, that itself is r naught. Okay, this is integrated rate expression. So we will make it more and more better, I mean, in terms of interpretation. Right. Now, this r naught bring here so that this become plus r naught, right? So minus r, let it be here, is equal to KT. Okay. So that this K is equal to R naught by R naught minus R by T. This is the expression for integrated rate expression for zero order reaction. We arrive to this expression, which is important. Okay. Now the interpretation, the various way it can be interpreted. So this particular equation, I will change the sign of it. Suppose this is R and minus KT plus R naught. So I have changed the sign of all the terms. Minus R has made as plus R. KT has become minus KT and minus R naught becomes this. Now this is an equation of the type y is equal to mx plus c. So any mathematical expression of this type if you draw the graph of it, it will be a straight line. It will be a straight line. So y-axis r, that means concentration. This is y-axis, right? Y-axis. And t to be taken in x-axis. Compare this. T to be taken in x-axis. Now this is a negative slope, means it should be downtrending curve like this. It is a straight line. It is a straight line. Y is equal to mx plus c is always a straight line. It is downtrending. I mean like this. Now slope of which can be determined easily now. Okay, slope anywhere it will be same, right? Because it is a straight line, right? So slope is equal to minus k. We can determine the value by slope. So these are the usefulness of integrated rate expression. By using the integrated rate expression, the method of calculation of the rate constant in terms of the rate of the reaction has become simple and accurate, right? So if you go with the definition, what is the rate of the reaction? For the first order, for the zero order reaction, rate itself is equal to k, rate constant. Rate itself is equal to rate because it is a to the power 0. A to the power 0 is 1. Let us do not consider this. Rate itself is k. What is k? Rate constant. Now, definition of the rate constant for the zero order reaction is initial concentration, final concentration divided by T. It is the change of concentration by time taken. Change of concentration by time taken is nothing but rate of the reaction itself, right? So these are the things that we can learn from the integrated rate expressions. Okay, we'll come back to the slides so that, okay. Okay. Yeah. Yes. Let us go on to that. Okay. Now the thing may not be very clear also, you can able to see now. So integrating the rate expression, dr is equal to minus k dt, r minus, so integration of 1 respects to r is r, and this minus r naught has come from integrated rate from the c is equal to minus kt. By doing this, we are going to get this expression, right? So I have derived it. I hope you can able to understand from it, right? So this is the expression for constant of rate constant. Okay, r naught minus r by t. Okay. Okay. So this graphically also I have explained you. Concentration of R versus time for a zero order reaction is a straight line. For zero order reaction is a straight line. Remember that for any it's not getting it. Okay. Yeah. Okay. First order reaction. Now, for the integrated, right? Change the color of the pen. Okay. Now remember, the concentration of R versus time is a straight line for zero order reaction. Suppose if you draw for any order reaction other than zero order, the graph is concentration of R versus time is an exponential graph. So graph is like this. So concentration of R versus time, we have shown in the earlier that this is the way, and the slope of the curve is rate of the reaction. But for the zero order reaction, it is a straight line. So this is being confirmed by integrated rate expression, right? Now for the first order reaction, R giving rise to P, what are the changes that we can make? Rate is equal to minus dr by dt is equal to k into r to the power 1, right? Then dr by this r is equal to dt minus k dt by changing that. I think this is very clear. Integrating dr by r is equal to minus k dt 0 to t. Now 1 by r dr, 1 by r with respect to r, integrating 1 by r. So integrating 1 by x dx is, this is ln x log x. Okay, ln, when we write in this way, ln, this is nothing but log to the base e x. Okay, it is log to the base ex. This is the way that we write, because in physics, mathematics, and chemistry, there are various ways of change of writing is there. Whenever you are writing ln, it is log to the base e. Okay, so this is ln r, 1 by r is ln r, right? And constant of integration is minus ln r naught. Okay, I will derive another step also, which is not being written here. So this is ln r, right? This is ln r. This is equal to minus k 1 dt is t itself, plus constant of integration, Suppose if t is 0, right? If it is t is 0, then this becomes 0. C is equal to ln r. ln r naught, it becomes naught when t is 0. Constant of integration is ln r naught, right? So this is being taken here. Plus ln r naught will become minus ln r here, so that this expression can be made use of. Okay. Okay. So constant of integration is taken here, right? Minus ln r naught. Okay. So ln r naught minus ln r is equal to kt, or kt is equal to ln r naught by r. Okay, log of a minus log of b is log of a by b, that formula. And therefore k is equal to 1 by t ln r naught by r. K is equal to 1 by t, or k is equal to, if you convert this into log to the base 10, then multiplication factor is 2.303. 2.303 by t log of 10 r naught by r. So this is the expression, right? This is the integrated rate expression for it, right? Okay, not working. Okay, fine. So discard here and use it. It's giving trouble. Movement of slides. Just come here. This needs some adjustment. In Chamarajanagar. Some problem is that this is not doing it. Int. And it's not being changed. Shall I switch off the video? Yeah. Now it is coming. No worries. Yeah. Okay. Fine. Okay. So integrated rate equations. Okay. Integrated rate equations can be written in this way, right? K is equal to 2.03 by T log of 10 to the R0 by R, right? So the various ways that it can be written, log of R0 by R is equal to KT by 2.303. Now in this expression, okay, in this expression, if log of R0 by R is taken, log of R0 by R is taken, this is a having this kind of curve, okay, and slope is equal to K by 2.303, okay. So the various ways the equations can be written, that is the thing here. So log of R minus, okay, log of R is equal to minus KT plus log of R0. This is the expression from which we have derived this, right? Okay, I can further tell you about how this equation has come, right? So log of R naught minus log of R naught minus log of R, therefore is equal to KT. Okay. So log of R, I have changed the sign here. The minus sign has become plus sign when it comes here, and minus KT is plus KT. Okay, therefore K is equal to log of R naught by minus log of R by K. This is how the expression has come. So this is the expression is basic for deriving this. Now this is of the form y is equal to mx plus c. Always compare this. Therefore, when you draw the curve, or when you draw it in graph, log of R, this is log of R, y-axis, x-axis t. So this is having negative slope. Okay, this will have the negative slope like this. Okay, if you take this equation and draw the graph log of R versus t, the graph is like this. Modify this expression, log of R naught by R is equal to KT by 2.3. Now this equation also is of the type y is equal to mx plus c. See how beautiful it is. It can be compared with the type y is equal to mx plus c, where this is 0, where c is 0 here. So you have plotted log of R naught by R, log of R naught by R, okay, and is equal to mx. So t is in the x-axis. Therefore, what is left out is m, slope, and c is 0. Therefore, it is passing through 0. So it is passing through 0 because intercept is 0. C is the intercept. Okay, intercept where it y-axis it touches. So 0. M is the slope. Therefore, slope is equal to, in this case, slope is equal to K by 2.303. Slope is K by 2.303. What is the slope here? In this expression, what is the slope? Slope here is minus K. In this expression, slope is minus K. So, any mathematical expression, you try to write it in the form y is equal to mx plus c, it becomes easy to interpret in the graph. And the graph related questions can be solved by doing so, right? Okay. Okay. So this is the thing. ln r, log of r by t is a slope, right? So just now I explained this. Now half-life period. Half-life of a reaction is the time in which the concentration of the reactant is reduced to 1/2 of its initial value, represented as T half. Why this concept of T half? Because time required for completion of the reaction is not known. because the reactant becoming zero is not found, because there is always an equilibrium state in which the reactant will never become zero. Therefore, it is better to take the half-life period for the meaningful conclusion. The half-life period is time required for half of the initial concentration to be reduced. I mean, if 10 moles of a substance is being taken, 10 moles of a substance is taken, and it is the reaction has started. So after start of the reaction, the time required for when it becomes 5 mole, when the reactant becomes 5 mole, that is the half-life period of that particular reaction. That is the half-life period of the reaction, right? Okay, TF for zero order reaction. What is the TF for zero order reaction? We have the expression K is equal to R naught by R by T. For at T is equal to T half, when the time is T half, the final concentration is half of the initial concentration. As I given the example, 10 mole becomes 5 mole, half of the initial concentration. Therefore, written as R is equal to final concentration is half of initial concentration, and K is equal to R naught by half of R naught. Therefore, if R is replaced by half of R naught, then 1 minus half is half. Therefore, R naught by 2K. So this is the expression for half-life period. Okay. So it is clear that T half of a zero order reaction is directly proportional to initial concentration. T half is directly proportional to initial concentration. We can able to understand from this. So T half for the first order reaction. T half for the first order reaction. Now we have to take the expression for the first order reaction. Now T half is equal to R is equal in the case where T half R is equal to R naught by 2. Therefore, K is equal to 2.303 by T half. When the T is T half, this R naught is initial concentration, and the final concentration is R naught by 2. This is R naught by 2. This is R naught by 2. So R divided by R naught by 2. 1 divided by half is 2. That is log of 2. Log of 2 has the value 0.301. And 2.303 into 0.301 is 0.693 divided by K. This is how we have derived T half for first order reaction. So thus the first order reaction half-life period is constant. It is independent of initial concentration. Very important thing. It is independent of initial concentration. Right? So there are some reactions. Okay, before going to the pseudo first order reaction, we have derived some mathematical expression that you're supposed to remember. So most of the questions in this particular chapter is from this particular expression. So for zero order, okay, for the zero order reaction, K is equal to R naught minus R divided by T, right? And T half for the first zero order reaction is R naught by 2K. This is for zero order reaction. First order reaction, for the first order reaction, K is equal to 2.303 by T log of R naught initial concentration by final concentration. Initial concentration by final concentration. So this is, and the T half for the first order reaction is, okay, this is 0.693 by K. 0.693 by K. So R naught is not there here at all. Okay. So these are the mathematical expressions you should remember, recall, write it boldly, or practice this. Okay. So there is a chance of asking the derivation also, but it is not being asked in a few years. About 3 years, we didn't find the question of derivation of this expression in the CBSE examinations. But using these expressions, how to solve is being asked, right? So remember this for the zero order reactions, and first order reaction, and graphical interpretation. These are important. Graphical interpretations are important, right? Right. So the reactions which are not truly first order, pseudo first order reaction means they are not truly first order, but under certain conditions, the reaction becomes of first order. It becomes a first order, are called pseudo first order reaction, pseudo unimolecular reaction or pseudo first order reaction, right? Example is hydrolysis of an ester is an example of this. Okay. This is ethyl acetate or ethyl ethanoate with H2O. It gives acetic acid and ethanol. Okay, it is hydrolysis of an ester is a reaction which is pseudo first order reaction. Okay, why it is so? Let us try to know about it. The reaction occurs in a very dilute conditions because it is a covalent bonding is to be broken by the polar water. It is a slow reaction, slow process because more water is being taken for that. So suppose if the time t is equal to 0, you have taken 0.01 m solution. Suppose if you have taken 0.01 m solution, so it contains 0.01 mole of ester, right? And the H2O in 1 molarity, 0.01 molarity means in 1 liter of water you have taken. 1 liter of water is almost 1 liter of water. Of course, the volume, it is a volume. Almost 1 liter of water, that means 1,000 grams of water. 1,000 grams of water means 55.5 moles. Here it is taken only 10 moles. It is 55.5 moles of water is being taken, right? 0.01 mole of ester is in 55.5 moles of water initially. And at the time, okay, when suppose if it is completely reacted, say it becomes 0 mole. So this becomes 55.5 minus 0.01. Okay, so this is 55 point. Okay. So this has become 55.5 minus 0.1. It's a very, very small number, right? So it has not changed at all. That means it has not changed. The H2O concentration is not changed. Suppose the rate of an expression is equal to K into an ester concentration into H2O concentration, but H2O concentration is not changed at all. Therefore, the rate can be written as rate is equal to K dash into concentration of an ester itself, because this is to be brought here, rate by H2O, concentration of H2O is K dash. Okay, or K into H2O is K dash. K into H2O is K dash, another constant, because H2O concentration has not changed. Therefore, now the only concentration term 1 is there, H2O to the power 1 is there, therefore it is a first order reaction. Okay, it's supposed to be second order reaction because of the concentration of H2O also to the power 1, but it is a pseudo first order reaction because of this reason. Okay. So how to find out methods of determining, we'll take up methods of determining the order of the reaction. Methods of determining the order of the reaction, right? So there is graphical method. Graphical method is used for determining, or we can make use of the mathematical expression. Mathematically, we can able to do. That means integrated rate method we can able to use, right? So using the expression, or half-life method, we can able to determine the rate of the reaction. Let us see one by one how this order of the reaction is determined, right? So graphical method or graphical interpretation that you have to understand. This dx by dt plotted versus concentration. For a zero order reaction, this is so. Rate, this is nothing but rate of the reaction. Rate of the reaction is same whenever the concentration is changed. Concentration of first order reaction, rate increases with increase in concentration. First order is affected by the rate. And dx by dt versus concentration square. Here concentration square for the second order reaction, it is written like this. Rate is a graph like this. Rate increases with increase in concentration, right? This is another way of graphically determining. Concentration of A versus T is a line, straight line for a zero order reaction. But instead of concentration A, we have to take log of A versus T for the first order reaction. So it is also a straight line. So slope can be determined. Okay. And for the second order reaction, 1 by concentration of A versus T is a straight line like this. 1 by A, we have taken 1 by A, it is a straight line. By this way also we can able to determine by this way we can able to find out order of the reaction or rate constant of the reaction. Temperature dependence of rate reaction. Next part of it is temperature dependence, how the temperature changes the rate of the reaction. Let us take up this. Most of the chemical reactions are accelerated by increase in temperature. That is what we observe. Most of the reactions are accelerated by the temperature. So example is decomposition of N2O5. First, the time taken for half of the original amount material to decompose is 12 minutes at 50 degrees Celsius, 5 hours at 25 degrees Celsius, and 10 days at 0 degrees Celsius. Look at this. 12 minutes at 50 degrees Celsius, 5 hours if this is half, temperature is half. So it depends upon the temperature, how the temperature affects, right? So it has been found that the chemical reaction with the rise of temperature by 10 degrees Celsius, rate constant, the K value is doubled. The temperature difference of a chemical reaction can be accurately explained by Arrhenius equation. Okay. So remember, we have rate law expression, right? K into A to the power alpha and B to the power beta. So the change of concentration, how it affects the rate can be determined by rate law expression. It is constant, the K is constant for a particular temperature. If the temperature is changed, the rate constant value changes. Thereby rate changes. Rate changes because rate constant value changes. This increases with increase in temperature. Rate constant increases with increased temperature because rate constant, what we have seen is increased temperature, increased effective collisions increases. Thereby, the rate of the reaction increases. The temperature, how it affects, let us try to see from, okay, graph also. So this is being given by Arrhenius equation. The Arrhenius equation, the rate constant and the temperature, how these two get changed, it can be understood by this. K is equal to A into E to the power minus A by RT, where A is called Arrhenius factor or pre-exponential factor. E to the power minus EA by RT. EA is called activation energy. EA is called activation energy. It is one term, not E into A. It is EA divided by RT. Okay. Now, this Arrhenius factor depends upon the reaction. Okay. So it is a characteristic of that particular reaction. A. It is a constant for the particular constant throughout, right? And this E to the power minus EA by RT, this is fraction of molecules having energy more than the activation energy, Now, what is this activation energy? We have to know that. The activation energy is the minimum excess energy required for the reaction to occur. Okay. Suppose in a graphical way, if I have to explain, it is a reaction coordinate, and this is the reaction, this is the energy of the reactants, and this is the energy of the product. Energy of the product is usually less than the reactant, so that it is an exothermic process. It occurs on its own. But the energy to reach from reactant to product is like this. There is some amount of energy required. This difference is EA. Activation energy, minimum excess energy required for the reaction to occur is called activation energy. And this activation energy is, to reach the activation energy, you need more and more temperature, right? Therefore, this e to the power minus A by RT, exponential e to the power minus E by RT will give you the fraction of molecules which is having energy more than this. Only when this having cross over this energy barrier, then the reaction occur. Therefore, this expression will give the relationship between K and T perfectly. Now, whether temperature increases, K value increases, let us know from the point of view. If T value increases, since it is in the denominator, 1 by T value decreases. So total value decreases. 1 by T value, because it is the denominator. If T increases, 1 by T decreases. But minus 1 by T increases. Minus 1 by T, because negative sign, if you give, it increases. So e to the power increases. E to the power increases, then K increases. Therefore, temperature increases, K increases. Right? So this is the way we have to interpret. So here R is the gas constant and EA is called activation energy. Okay. So let us know the activation energy from the transition state theory. According to Arrhenius reaction takes place through the formation of unstable intermediate complex which exists for the short time and then breaks up to form product. So this is a transition theory. Suppose if it is H2I2 giving rise to 2HI, so the transition theory says that when H2 molecule and I2 molecule come closer, there is a covalent bond between 2 hydrogen and covalent bond between 2 iodine. But when they are closer, okay, this H and I can also form an intermediate bond. And this bond is not completely lost. Okay, so that this forms an intermediate like this. The formation of the intermediate is a must for the reaction to happen. So this needs energy. Formation of this needs energy. Therefore, we need more energy to start with, and therefore the reaction occurs. This is a transition state. Okay. So this is the reactant, energy of the reactant, and this is the energy of the product. And this difference is activation energy. And this is threshold energy. This is called threshold energy. Okay, minimum energy required is called threshold energy. The minimum excess, the difference, the minimum excess energy is called activation energy. Okay, so this is how the theory is explained. Suppose if you use a catalyst, it follows different path. This is the path of the reaction coordinate. So it follows another path in which activation energy required is less. Thereby, it fastens the reaction. It increases the rate of the reaction. Right. So activation energy is energy needed from activated complex is called energy of activation. It is very low for some reactions and very high for others. What do you interpret if the activation energy is very high for a reaction? So if it is very high, then the reaction is not going to happen at all, right? So if the activation energy is low, then it is possible, right? EA is always positive, activation energy is always positive, and the larger the value of EA, slower the rate of the reaction at a given temperature. Okay, these are the very important conclusions. The larger the value of EA, steeper the slope, and ln versus 1 by T. Steeper is the slope, then it is not possible state, right? The high activation energy corresponds to a reaction that is very, very sensitive to the temperature. Okay, the high activation energy corresponds to a reaction rate that is very, very sensitive to temperature. Okay. Now let us see from the energy coordinate point of view. Suppose you have kept some molecules, you have taken some molecules for the reaction in a closed vessel. There are some molecules which are reacting molecules, right? So there may be two different kinds of molecules or so. Now, from the kinetic energy point of view, if the gaseous phase that you take, if you gaseous phase you take, the reaction, all the particles of the gas are not moving with the same energy, right? They are not having same kinetic energy, right? So they are moving with the different energies. Therefore, for a gas, from the model of gas, we have that average energy concept, the average energy of the gas molecules. Some gas molecules are moving fast and some molecules are moving slow and all that. Okay. So whenever they are moving, they are colliding each other, and perfectly it is elastic, so that energy is being not lost. So energy transfer from one molecule to another molecule is also there. But while transferring the energy, it is not being lost, and they are moving randomly, transferring energy to the one molecule to the other molecules, but the average energy remains constant. So if the fraction of molecules means some fraction of the molecules are having less energy. This is the less energy. Some fraction of molecules are having this much energy. Okay. So the kinetic energy, the sum of this much fraction of molecules, are having this kinetic energy. Okay. In a vessel, there are many molecules following average energy. And some molecule, some fraction, less fraction of this, is small fraction, are having, small fraction of molecules are having higher energy also. Okay. So this is how we can able to compare any, even for the human beings also in a sample. Some are very intelligent, or some are reactive, or they give the expressions, or they respond, right? And some fraction of them are dull, or they don't participate, all such things. Even the human beings in a particular classroom, we can say the same way. There are many students who are average. So if the marks are being plotted, also you may get such a kind of graph, right? Now this is the case when temperature is T degrees Celsius. Now suppose if it is a T degrees Celsius, and if you increase the temperature T plus 10 degrees Celsius, the fraction of molecules are not changed, therefore it becomes flattened. But the molecules having more energy is increased. The molecules having more energy, it flattens means it is extended, right? So the average energy is changed. This is the average energy earlier, and this is the average energy later at T plus 10 degree. When you increase the temperature, every molecule absorb energy, but some molecules to the greater extent absorb energy, right? Therefore, the average energy increases when you increase T plus 10 degrees Celsius. Now, suppose if this is the activation energy, means energy required for the reaction to occur. All species or all the particles which are having less energy cannot able to participate in the reaction at all. Okay, they should possess that much energy, so that with that energy, if they collide, probably they bring about the reaction. Now at T plus T degrees Celsius, only these molecules were qualified for the reaction. When you increase the temperature, again this many molecules are coming in the net. I mean, so that this, when you increase the temperature, more number of molecules will qualify for the reaction. Okay. So what we find is, if you increase 10 degrees Celsius, the area that added is almost the same as the area. I mean, the total area is doubled. Total area in the curve is doubled. Area under the curve is doubled. We mean that 10 degrees Celsius, the rate of the reaction is doubled. Okay. So it is clear from the diagram that the curve T plus 10 degree, the area of showing the fraction of molecules having the energy equal to or greater than activation energy, gets double, leading to doubling the rate of the reaction. Okay. Now the chemical reactions with rise in temperature by 10 degrees Celsius, the rate constant is nearly doubled. The ratio of rate constant at T plus 10 degree divided by at K temperature, the K at temperature is called temperature coefficient. The temperature coefficient, this N value, is from 2 to 3, right? Okay. So Arrhenius equation. So let us see some more questions, and in the next lecture when I come there. Okay, so the mathematics expressions that we have derived are important. The reintegrated Rayleigh law expression for zero order and first order, try to remember that, and also the Arrhenius equation, right? So based on that, what are the questions which can be asked, and objective type questions we'll see in the afternoon, right? Thank you.
Thank you, sir.
Thank you. Thank you. Bye.
Thank you, sir.
Thank you. ಇದ್ರೆ ನೀವಲ್ಲಿವರೆಗೆ ಭಾಗ್ಯ.
ಹಾ ಸರ್.
Okay. This is not going. That's all. It's not at all. Okay. Yeah, now it is possible. So